Okay, this is discussion question 1. I'm going to go over a couple things here. So it gives you two circuits, and you're looking at the one of them has an ammeter one of them is an ideal circuit, so it has an ammeter with no resistance, and one of them is probably more of a normal circuit, it has an ammeter with some resistance, but hopefully not enough to affect the circuit too much. So the first thing you do is you graph. You look at you're going to sketch what each graph would look like with current as a function of voltage, basically. So as you change the voltage, this voltage of the power source, it's a variable voltage source, which you can tell by that line through it. And of course, it tells you that too. Right, so basically you can look and pretty easily tell that if all things being equal, of course, this is going to have the higher resistance. Okay, so if it has a higher resistance, you could say, V equals IR. Well, how does that look in equation form? The I is over here, because that's, if you say Y equals MX plus B. So you say Y equals MX plus B. The y-intercept's not going to matter here, but then you would have, you're graphing current on the y-axis, so that'll go over there. And then you're graphing voltage on the x. Well, if you rearrange current Ohm's law, you have I equals V over R. So you could write it as I equals 1 over R times V. So your slope is going to be the inverse of the resistance. So that means as the resistance gets higher, you're actually going to have a lower slope, right? Because you're doing the inverse of it. So 1 over 10 is smaller than 1 over 5, or whatever, however you look at it. So your first one you should have sketched the steeper slope, and then the second one should have been the lower slope, because you got more resistance here. All right, most of you did that right. I just wanted to make sure I covered it. All right, next part, it says let the potential difference be, it gives you all this stuff. Basically, you're writing the loop rule, Kirchhoff's loop rule. Conservation of energy is always the loop rule, which basically says that the voltage as you go around has to equal 0, meaning the voltage sources will give you voltage, but all the other stuff has to use it in one loop. So if you look at the first circuit, for instance, in this loop, as I go around, say I start here and end here, this will be my starting point. Same thing here. As I make a loop, I go through these different circuit elements. Okay, so on this one, I'm only going through 2 elements. I go through the battery. So I say the sum of the voltages has to equal 0, basically, meaning I get voltage gain here. So this would be delta VPS minus IR. Right, and where do I get IR? Well, IR, voltage is IR. We're writing the loop rule, so we only care about voltage. We have to write it voltage in terms of what we're given, though. We can't use V, so we have to use IR. In this case would be I big R. Okay, so you can write that like that, and then on this one you go through the battery. So this is delta VPS minus I little r minus I big R. You notice if I go across a battery with the current, the direction of the current is like that. Then I gain voltage if I go across the resistor with the current. It's a voltage drop. So anytime I go across the resistor, you'll see it as minus. So some of you wrote yours like this, and that's good. You could also have written it like this, a little more simple. You could have just done like this. You're just rearranging the equation. So this would have been I big R plus I little r. Could have written it like that as well. All right, so then explain how they account for any difference between graph 1 and 2. Most of you did this, I guess, satisfactorily. I mean, you have more resistance. You can easily tell that the loop rule equation provides for more resistance in the second one, and more resistance is this lower slope. So you should have made some explanation as to that. Okay, so I'm just going to get a check mark there. I'm not going to write it out. All right, now for the workout part, it tells you that in circuit 2, R equals 40 ohms, and then it gives you the voltage across the resistor in the circuit. So, and then it says find the little r, right? So I'm going to redraw circuit 2. Right, so this is R, big R. This is 40 ohms at 2.5 volts. And this is 3 volts. That's to the power source, right? So that means, of course, the little r is going to have to get, we don't know what it is, but we do know it's going to have to get the other 0.5 volts to satisfy Kirchhoff's loop rule, right? So this is going to have to get 0.5 volts across it. This is getting 2.5 volts across it, because it's got to add up to the total voltage. Okay, so it says calculate the internal resistance of the ammeter. Well, to get resistance, I'm going to need to know voltage and current. Well, I know for the individual resistor, I should write that as a, you know, what it gives it. So little r is going to be V over I. Any resistance is the voltage divided by the current across and through it. So we know this is 0.5 volts. Okay, but over what current value? Well, it's a series circuit, so if I know the current anywhere, I know the current everywhere. And in this, right here, I know that I is equal to V over R, so it's going to be 2.5 over 40. 2.5 over 40 gives you 0.063. All right, so that means that I is equal to 0.063 amps. That's going to be the same everywhere, so that will go up here. Right, and that will give me the resistance value, 0.063. So 0.5 divided by 0.063 should give me about 8 ohms. And that's what I'm going to write it as. Okay. If you did it as 0.0625, which is what you get exactly 8 ohms. So R should be 8 ohms, little r. And that value will stick with little r forever. So now it says that you're replacing this other voltmeter with another resistor, and you're going to have to find the equivalent resistance. Well, remember, these are in parallel with each other. So you can redraw the circuit if you want, and let's see, so if I redraw the circuit, this is R, big R. Well, I should just let's put the values that we know. So this is 8 ohms. 40 and a 120 in parallel. So 40 to the negative 1 plus 120 to the negative 1. You get 30 ohms. Right? 3 volts still. Yeah. So this is 38 ohms. Says what is the equivalent resistance of the circuit? Well, that's going to be, these are in series. So 30 plus 8, so it's 38. All right, now take all that into account, and then it says calculate the current in each of the resistors that are in parallel. So you got to find the total resistance. Okay, all total, and not total resistance. You need to find the total current so that you can find the individual currents through the branches. So remember, in a circuit like this is a combination circuit. In a circuit like this, you're going to current's going to come out the positive side, and it's going to branch off and go through here. Okay, so we need to know what is that total current going to be, so that we know how much voltage each one of these is getting. Okay, if we know that, then we can find the current through the individual resistors in parallel. Okay, so what voltage is this getting? Well, V equals IR. We need to know that I value. So remember, I is going to be V over R. So it's going to be 3 over 38. right? Because the total, it's 0.079, so I is your total current. Doesn't ask you for that, but you need it to find the voltage across this resistor, which is the combination of these resistors. Okay, so this is going to be 0.079 times 30, which is 2.37. Okay, so this is going to get 2.37 volts across it. Of course, that'll get the rest, but we don't really care. And if this resistor is getting 2.37, that means both of these are getting 2.37 volts. So to find the individual current for each one, it'll be, so let's say it's V over R, so 2.37 volts over 40 is roughly 0.06 amps. And then you do the same thing, 2.37 volts over 120 ohms. And that'll give you the rest, about 0.02 amp. Okay. So that's what you roughly should have gotten on that discussion question. All right, remember, if you have any questions, let me know.